Hello, here's another trio of waves questions. So we start here. Figure 4.1 shows the variation with time of the displacements xs and xt at point P of two sound waves s and t, right? So they've given us two wave profiles. We've got time on the x-axis and it's at a particular point in space. By reference to these two profiles, state one similarity and one difference between these two waves. Right, let's say then that the similarity is that they've got the same frequency. That's certainly apparent from the graphs, and a difference where they're out of phase. So we'll say they've got, well, you can just say they've got a difference in phase. The difference is their phase is different. We just had to state, didn't we? Yeah, so that's fine. Explain whether or not the two waves are coherent. So now we need to state that yes, they are coherent, but we need to say why, which is that they've got a constant phase difference. Because remember, that's our definition of coherence in A-level physics. We don't get onto spatial coherence until later on, so that's good enough for there. Speed of the sound waves, 340 meters per second. Determine the frequency of wave S and its wavelength. So the frequency is 1 over the period. The period is 3 milliseconds. So we've got 1 over 3 times 10 to the minus 3. So that's going to be 333. But we've got 2 sig fig there. And we're reading something off of a graph. So let's say 330 hertz. And then what do we need? The wavelength. So the wavelength is the speed divided by the frequency. So that's 340 divided by 333. So that's going to be 1, and then we need another 7, which is getting on for 200ths of this. So let's say 1.02 on there, which would be, just saves me getting the calculator, which would be 1 meter to two significant figures again. So that all the way through. At point P, the two sound waves superpose. By reference to the graphs, determine the resultant displacement of the two waves at t is 1.5 milliseconds. So at 1.5, we're here and here. So we're going to have displacement is going to be 0. And 2.25. So what's 2.25? Oh, that's where we got the peak and the trough, isn't it? So yeah, we got there and there. So what have we got? That's 3 micrometers and minus 2. So it's going to be 1 micrometer. Okay, this is so far so good. The intensity of wave S alone at point P is I. So remember that intensity is proportional to amplitude squared. Show that the intensity of wave T is 2.25. Right, so so what have we done with the amplitude? We've multiplied that by 1.5. Then that means we're going to get 1.5 squared as a multiple of the intensity, which is 2.25. So that is good. Then we've got calculate the intensity of the resultant wave. Oh, right, okay, the intensity. Actually, I should probably put the I into this. So if we've gone from I, so yeah, we can say intensity for wave S will be 2.25 I for wave T. It's just worth putting that in. If I for then that. Right, okay, calculate the intensity of the resultant wave. Right, the resultant wave is now, it's gone down to 1, so it's halved. So that means that we're going to have A is times a half, so the intensity is times a quarter. Therefore, we're going to have I divided by 4. That was a nice starter question, covering quite a lot of ground. Right, where's next? Oh, we're still on the same question. Right, okay, keeps going. Part F. The sound waves shown in figure 4.1 are emitted by the loudspeakers labelled S and T, and they're detected by a microphone at point P. Right, okay. Calculate the distance that loudspeaker S must be moved towards P to bring the two waves into phase. State your reasoning clearly. So, well, we need a pi phase shift. therefore we got to move it by half a wavelength. Therefore, move by lambda over 2. That was 1.02, wasn't it? We calculated before. So 0.51 meters. Right. Describe how the intensity of the sound wave detected at P varies as loudspeaker S is moved in that way. So the intensity will increase to a maximum when S has moved 0.15 meters. So it will just keep on increasing and it hit a maximum value as soon as they get in phase. Right, now we have finished that question. So good. Next question, define the terms wavelength, frequency and speed used to describe a progressive wave. So wavelength, let's say for that is the minimum distance between 2 points oscillating in phase. Minimum distance between 2 points oscillating in phase. We'd probably say on the same wave, just to be super clear on what's going on. Frequency is the number of oscillations at a point per unit time. So number of oscillations at a point on the wave. Just keep putting that on the wave thing per unit time. And then speed. So the speed is going to be the distance traveled by the wave per unit time. Distance traveled by wave per unit time. By wave per unit time. Right. Hence derive the wave equation, which relates these terms together. Right. This always seems like it's so obvious that what is there to say? So we can say, well, in 1 second, we get F waves produced, each of wavelength lambda, lambda. So therefore, the distance traveled by wave in 1 second equals F times lambda. Cool. So providing you've got something along that line, then you'll be all right. It always seems, as I say, like you're writing out the blatantly obvious when you're dealing with that. But I've used up most of the screen already, so I have to cut down on my writing for the rest of it. Part B, explain what is meant by infrared radiation. Right, you can say two things about it. So first of all, you want to say it's electromagnetic radiation and then give some indication of the wavelength or the frequency, but wavelength people normally think of first. So you could say that it's got a wavelength. Well, let's give a range. So you could say the wavelength is somewhere in the region of 10 to the minus 6 to 10 to the minus 3 meters, something like that. Yeah, providing you've given a sensible range or a sensible value, then they're not going to be too fussed on this. I mean, you can take the wavelength up to the 7 times 10 to the minus 7. That's about as long as you could go. All right, so 10 to the minus 6 ain't going to be that great, is it? Oh no, it is all right. That's the shortest you can make the wavelength, is the 7 times 10 to the minus 7. You don't want to go any shorter than that. So that's why I went for the 10 to the minus 6. And then just make it longer from there. Yeah, providing you come up with a vaguely sensible number, you'll be all right. For infrared radiation emitted at a frequency of that, calculate its wavelength. So because it's electromagnetic, then we're going to want to say what a wavelength is going to be 3 times 10 to the 8 divided by 6.7 times 10 to the 13. And I want the period. So the period is going to be 1 over the frequency. So 1 over 6.7 times 10 to the 13. So what's that going to be then? That's going to be 1.5 times 10 to the minus 14. that one. This is going to help. I just don't want to get the calculator out, but this is going to help. So that's in seconds to work out this. So all we have to do is now multiply that by 3 times 10 to the 8. So that would be 4.5 times 10 to the minus 6 meters. Right, okay, that saves digging the calculator out. Infrared radiation is absorbed by molecular ions in a crystal, causing them to vibrate at that frequency. The amplitude is this. Sketch the graph. Right, so we know that we've got this period of 1.5. Oh, and I've put the 10 to the minus 14 there. So our period is here. So that's got to be one oscillation. So we're going to be halfway along there. And the amplitude is 8, because they've given us a 10 to the minus 12. So let's put then the, if that's also the crossing point, oh God, this is going to be maybe there, is it? It's hard to, oh no, it's going to be a 7.5, isn't it? So it's going to be a bit along from that. So say there, and then where are we? Say, yeah, here. Try and draw that in as a wave, then repeat. And then back down, and then yeah. So providing you're getting, you've got to make sure you got your amplitudes right, and if you mark on the crossing points, then you won't do too badly with that. I'm actually quite pleased with that for me on this screen. Is that this question done? Yes, it is. So one more question to go. Interference of waves from two sources can be observed when the waves are coherent. Explain the meaning of interference and coherence. Right, so interference, let's start with that one first of all then. So interference, there's quite a lot of things we want to say with this really. So let's start off with, first of all, so we got when two or more waves meet at a point in space. Or actually, let's not have, let's go with superpose, because that's an even better bit of terminology, bit of technical terminology. Meet at a point. They interfere. So we've stated when it happens. Now we just need to say what happens. So we're going to say is to produce a resultant wave. And it's all to do with displacement. So with displacement, which I'm just going to abbreviate to that, equal to the vector sum of displacements of the individual waves. So it's quite a lot to say. I mean, you might be able to write it out with less, but they can be so picky when it comes to giving out the marks on these sort of things. Coherence is less of an issue, as we've already seen in the first question on this. We just need to say there's a constant phase difference, and then we'll be all right. So constant phase difference between the waves. Right. Yes. Actually, you're saying here, oh, interference of waves from two sources can only be observed when waves are coherent. I mean, that's not really true. I mean, I suppose if they're saying they want to have a stable interference pattern, I mean, it didn't strike me when I first read the question. But you always observe, they always interfere, even if they're not coherent. You're still going to get interference. It's just going to be an unstable interference pattern. So I actually don't like the wording of that question at all, because you're still going to observe it. You're still going to see things changing because of the interference of the waves. So yeah, that's a bit rubbish, really. Right, part B then. Let's just push it on. Excuse me, something's stuck in my throat. Figure 6.1 shows two microwave transmitters. Usual thing, right? Is there anything that they haven't given us? That's in the question, in the diagram. That's in the diagram. Right, there's the wavelength. That's the thing that they haven't put in the picture. So let's just make a note of that here then. And that's everything out of the text. Use the idea of path difference or phase difference to explain how the interference pattern is formed. Right, we've done this sort of thing loads of times. So if the path difference is equal to n times lambda, where n equals 0, 1, 2, etc., etc., then we're going to get constructive interference and a maximum intensity. Then we've got the one that sometimes people struggle with a bit more. So if the path difference is, because we now want to make this an odd number of half wavelengths. So we need to get ourselves an odd number and then multiply it by half a wavelength. So we want an odd number is 2n plus 1, multiply it by half a wavelength, again for n is equal to 0, 1, etc., etc. Then we're going to get destructive interference and minimum intensity. Good, good. Calculate the separation between one region of high intensity and the next along the line. Right, so this is using our usual AX over D thing. So we want to get X, which is going to be lambda D over A. Lambda, they told us, was 30 millimeters, so 0.03. D is 5. A is 0.2. So we're going to have, what we're going to have on that, we're going to have, so that's 0.3 over 0.2. So that's 1.5 divided by 10. So 1.5 times a half is 0.75. No, yes, 1.5 times a half is 0.75. Yes, that's right. Right, so that was a nice little calculation. State the effect, if any, on the position and intensity of the maxima when each of the following changes is made. Right, so we just have to state again. So amplitude is doubled. So we've got position unchanged and the intensity will be times 4. Separation between the transmitters is halved. So that means we're going to get the intensity is unchanged, but the separation of the maxima, so the distance between the fringes, is going to have to double if we've halved the separation, because that stayed the same, that stayed the same. We've halved this, so we must double that. So we need to say X is times 2. And then the last one, the phase of transmitter A is reversed. So there's now a phase difference of 180 degrees. So again, the intensity is going to be unchanged again. But now we're swapping maxima for minima, because we're going to be, we're going to be out of phase when we're meeting at this midpoint. So previously we were going to get constructive interference whenever we had a path length, a path difference of a even number, a whole number of wavelengths, but that's just going to keep them out of phase when we're doing that. So all of these ones are now going to be our destructive interferences. So we're just swapping these labels, constructive and destructive, really, now that they're all out of phase. So everything, all our maxima and minima are going to just swap over position. So, but the intensity doesn't change because we haven't actually changed anything to the amplitude of the transmitted waves. So we've done that sort of thing. I mean, like, this question comes up so often. So you want to make sure that you've got all of these descriptions nailed. I mean, hopefully they'll ask the first part in a better way than this, because that is kind of misleading. But otherwise, these are just the repetitive descriptions that, yeah, always coming up on waves. There's not many things they can actually ask about in waves. So this double slit or double source microwave transmission is just so common, it's essential. Right, so that's those 3 done.